Hello, in this video I'm going to talk about the Michelson-Morley experiment, which is possibly the most famous, in inverted commas, failed experiment in the history of physics. Now, we don't look on it now as being a failed experiment, but at the time a lot of people saw it that way because it didn't produce the result that people expected. Now, we look at it now as being fundamental in part of that change, that transition from classical to modern physics at the beginning of the 20th century because of the null result that it produced. Right, well, before I get on to the actual details of the experiment, let's go back to the time at the late 19th century and just set some context of what people were trying to achieve here. So in the late 19th century, light was well described as a wave. And waves were thought of as having some medium that was oscillating and then allowing a wave to propagate through that medium. So think of water waves. You've got water, the water oscillates, and then the wave propagates across the surface of the water. And people were thinking a similar thing with light. If you've got light propagating, well, wherever it may be, but say, because it seems more confusing, say from the sun to the earth, or from distant stars to the earth, and this light is propagating through space. Well, what is the medium that light is actually propagating through? What is the stuff that's oscillating? And this is what people were on the lookout for. They'd given it a name. They'd called it the luminiferous ether. So you can see from the word luminiferous, if I can say it, that it's got something to do with luminosity, with light, and then ether, which may or may not start with an A. It doesn't matter if you put the A there or not. So this was seen as being this theoretical substance that was the medium that light was propagating through. And scientists, including Michelson and Morley, set out to try and discover this stuff, because if it's there, we want to be able to detect if it's there, and then we want to know how it behaves. So the thinking as a starting point of detecting it was to look at the relative motion of the Earth with respect to the ether. So we've got the sun, the Earth is orbiting around the sun, and you've got some distant star over here. Sometimes the Earth will be moving towards the star, sometimes it will be moving away from the star. So if you've got light coming out of the star, traveling through the ether at some speed, say the c, the speed of light, and we've got the Earth moving at some speed v in its orbit around the sun, due to the relative motion calculations that people were doing at the time, you're either going to get a relative motion of c plus v or of c minus v, depending if the Earth is moving towards or away from the star. Obviously, you get different numbers if you're in different points around the orbit, but just looking at that motion directly towards or away from the star, they're the relative speeds you're going to get. Now, Michelson and Morley are American scientists. This is Albert Michelson and Edward Morley. And Michelson had invented this thing called an interferometer. So an interferometer is like a beam splitter. So you've got a beam of light comes in and you've got a split mirror. So you put this mirror at an angle and it's part silvered. So you've got the part mirror, part glass, essentially. So half of the beam will get reflected off of the silver and half of it will go straight on. And then we can set up two branches then on this interferometer, the straight on, the longitudinal branch. You stick a mirror here, so the light will go straight through, hit the mirror at the end, reflect, and then come back. You've got the reflected, the transverse beam, so that gets reflected off, hits a mirror, comes back. You can make the length of these the same. I mean, you can adjust them, but let's say they're the same length, L. And then you recombine the beams. And you go off and you produce some kind of interference pattern, depending on how long it's taken to go along each branch of the interferometer. So the expectation that they had was, well, depending on where the Earth is in its orbit, or even how you orient the interferometer, if you rotate it around, so it's pointing in different directions, depending on the orientation or the position of the Earth in its orbit, you're going to get different relative velocity of the Earth with respect to the ether, and therefore with respect to the speed of the light travelling in the ether. So this is what they thought. And they thought, okay, well, different times a year then, or different orientations, we're going to get a different interference pattern when we stick the light through the interferometer. And the calculations that they were using for this, let's do a little bit of maths to show why they were thinking this. So let's look at the travel time for our longitudinal branch then. So on a longitudinal branch, we're going L out and L back. So we've got two routes. So we're doing time as in being our distance over velocity. Now so say the Earth was going this way at some speed v. So we're going to have these two relative velocities. On one direction, we're going to have a c plus v. And then on the other direction, we're going to have a c minus v. So we're going to have a c plus v. We're going to have a c minus v. So let's combine these into a single fraction. Our v's will cancel on the numerator, and we're going to end up with a 2l times c divided by c squared minus v squared. Let's rewrite this in a way that is going to be helpful for doing a binomial expansion. So we'll take a factor of 2l over c out, which means we've got a second fraction then of c squared over c squared minus v squared. Then let's divide in this second fraction, divide all of the terms by c squared. So you'll have 2l over c, and then we'll have 1 over 1 minus v squared over c squared. So you can see now in this second fraction here, this is just ripe for a binomial expansion. We got 1 minus v squared over c squared, all to the power of minus 1. Now, how many terms are we going to need on this? We're talking about the motion of the Earth around the sun. Okay, it moves pretty quickly in its orbit, but about 30 kilometers per second, something like that. So fast, but nothing compared to the speed of light, especially when you've squared everything. So in our binomial expansion, we're probably only going to have to do a couple of terms. So remember, these start off with 1 plus nx when we're doing our expansion. So we've got the 2l over c, and then we're going to have 1 plus nx. So that is going to be 1 plus, so we've got a minus 1 for n, and now x is minus v squared over c squared. So the minuses will cancel, and we get 1 plus v squared over c squared. So that's our expected travel time if we're going along the longitudinal branch. Let's do the same thing for the transverse branch then. The thing we have to be careful with the transverse branch is we need to do some vector addition on this, because of course everything's moving off to the right. So the mirror has moved both on the way up and on the way down. Both of these mirrors, this mirror here and our beam splitter mirror. So we need to do some vector addition, because we've got our vector component v of the motion of the Earth. We've got the speed of light on the hypotenuse. We're interested in the perpendicular component. So using our Pythagoras on this here is going to be the square root of c squared minus v squared. So, but the travel time is going to be the same whether we're going out or back. It doesn't matter. We haven't got any relative motion in the way that we have on the longitudinal branch. So total distance is 2l. Our speed is the square root of c squared minus v squared. So let's do a similar trick to what we did in the first calculation. Let's take a 2l over c factor. So that's going to leave us with a 1 divided by, so we've taken a c out of the contents of this square root here, or a c squared out, because it will root the c squared to be a c when it comes outside. So we're going to have the square root of 1 minus v squared over c squared, another binomial expansion. But this time we've got a power of minus a half rather than a power of a half. So when we do the binomial expansion, we get 2l over c, and then we're multiplying by 1 plus v squared over 2c squared. So it's the same as this travel time, except we've got this factor of 2 here in the denominator. So factor of a half overall. So this is why they were expecting to see an interference pattern that was going to be changing, because you've got a difference in travel time down these two branches if the branches are the same length. Now, the spoiler that I gave at the start of the video, they didn't see this result. they got a null result. They did not observe a difference in travel time, regardless of orientation of the interferometer, regardless of where the Earth was in its orbit around the sun, and therefore the supposed relative motion to the ether. They did not get these differences in the travel time. They actually got that it was always the same. Regardless of what they did, there was always the same travel time down both branches. And this caused considerable confusion. Now, people came up with various explanations trying to say, well, okay, maybe the Earth is dragging the ether with it in its orbit. So there's like a localized bit where there is no relative motion of the Earth with respect to the ether. But then other observations of positions of stars and such like didn't confirm this. It didn't support it at all. There was no agreement with these other independent observations. Because if the Earth was dragging the ether with it, well, you'd expect all other objects in the night sky to be dragging the ether with it as well. And none of that was observed. So there was a little bit of a, well, what do we do now going on? And then two chaps, so this is Hendrik Lorentz, who was a Dutch physicist, and then George Francis Fitzgerald, Irish Fitzgerald. They came up with a suggestion of, well, what if there is a contraction in length in the direction of motion through the ether? So if the Earth is moving that way through the ether, length appears to be shorter by some factor. And the factor that they were introducing into this, the Lorentz factor or the Lorentz-Fitzgerald factor, depending on what you want to call it, is this factor of the square root of 1 minus v squared over c squared. And they were saying, well, if you use this length contraction in these calculations, so changing all of these L's around and including these factors, I'm not going to do it all on here, but if you do, then all of the time differences cancel out, and at least it would match the outcome of the experiment. So this was one proposal, and over subsequent decades, it was this factor that then started getting built into what then became special relativity when Einstein put it all together. And I'll be talking about that more in the next video. And I mean, we were left with a conclusion really of this, that if we're getting this null result, well, either the ether doesn't exist at all, that's always a possibility, or it does exist, but we can't detect it. But even more than that, putting aside the issue of the ether, is then saying, well, we have to abandon this idea of absolute motion. Yeah, all of these calculations are based on the idea that there is some frame of reference where light moves at the speed of v, i.e. the frame of reference of the ether if it existed. So that's what we mean by an absolute motion. And then working out these relative motions based on this particular frame of reference. Now, this experiment was saying, well, there is no absolute motion. This just isn't the case. All observers are obtaining the same value for the speed of light, regardless of their own velocity. So regardless of whether the Earth is moving towards the star or away from the star, an observer on the Earth will record the velocity of light as being c. It doesn't matter what the velocity of their frame of reference is. And this is completely contrary, well, to these calculations that I've put on here, because they're based on the idea of Galilean transformations. So Galilean transformations we touched on a few hundred videos ago when going through our classical mechanics. So if you want to transform from one frame of reference to another frame of reference moving at a different speed, then there was certain, well, simple, what you'd describe as maybe being intuitive, common sense operations, mathematical operations for transforming from one frame of reference to another. These Galilean transformations are approximations. They don't work in all cases. We've got this factor that needs to be included in our transformations. We're now moving from Galilean transformations to Lorentz transformations. And the reason Galilean transformations work is, well, I mean, look at this factor here. If we're operating at relatively low speeds, as in our v squared is small, then this factor just reduces down to the square root of 1, i.e. 1. So whether you're multiplying it by, if you're multiplying by it or dividing by it, it doesn't make any difference. It's only when we start getting to frames of reference that are moving at very high speeds that this factor actually comes into effect. So Galilean transformations are still really, really useful in a lot of everyday situations, much as our Newtonian mechanics is still really, really useful. They're both approximations, but in an enormous number of situations, they are approximations that are perfectly valid. What we want to do now, and what we're going to do in the next few videos on special relativity, is deal with these cases of very high speeds. So moving from a rest frame, a frame of reference that is not moving, where we as an observer are not moving in that frame of reference, and then describing what happens in a different frame of reference that's moving at a very high velocity. So that's what we're going to be doing in special relativity, examining the effects of this Lorentz transformation on things like length and time. So contracting lengths and dilating or increasing times. So that's what we're hitting on next in special relativity.